Okay, now, are we going to get interference? Are we going to get interference? So I've got that ray of light that is going all the way like that, and I've got a ray of light that's just doing that. I've got the two rays. Are these two rays of light going to interfere? Well, we go back to our higher criteria, and it's just the same for advanced higher. The criteria which you will find for constructive and destructive interference is on the formula sheet, but it doesn't tell you which one's which. It's just a bit vague. And what it says is optical path difference, this is what's written on the formula sheet, is m lambda or m plus a half lambda, where m equals 0, 1, 2. Now that's not very helpful because it doesn't tell you which one's constructive and which one's destructive, but you're just going to have to remember this. This one is constructive interference. So if the optical path difference is a whole number of wavelengths between the two rays of light when they come back, if it's a whole number of wavelengths of light, then you'll get constructive interference. And if when you do the analysis it's involving a whole number plus a half, in brackets, number of wavelengths, then that is destructive interference. So it doesn't say constructive and destructive interference on the sheet. It only tells you those two. Okay, so that's a minor problem, but you should just be able to remember that. What we've now got to do is say, what is our optical path difference? Well, we know it's 2nd, and is there a phase change? So these are our two considerations. Consider, and hopefully you're writing this down. Consider what is the OPD? That's the first one. And the second one, that's a bit unfortunate, isn't it? Because we know that one's 2nd. The second thing, not related, is there a phase change overall? So these are our two considerations we have to think about. Okay. Right, so let's have a look at this particular example here, where the ray of light, this is very common, advanced higher, this one, the optical path difference compared with this one is 2nd. So what we're going to do is we're going to say, we'll do constructive first. We're going to take the formula off the sheet, and we're going to say that OPD has to be equal to m lambda. Now we know that for this particular reflective situation where a ray of light goes into a beam of block of glass and this beam doesn't, that OPD is 2nd, and that has to be equal to m lambda. That is our first bit. What is the optical path difference? It's 2nd. And is there a phase change? Okay, is there a phase change? And the answer is yes, there is, because we've done the this one, the low to high I. So there is a phase change there, and there isn't a phase change here. So I'm just going to cross it out and say it doesn't exist. So overall, between the two of them, we've got an optical path difference and a phase change. And so we're going to say there's the optical path difference. That's the first consideration. Is there a phase change? Yes, there is. So I'm going to add in my phase change. And I hope you're all with me so far. Now you'll see that that term has a lambda bit in it, and that term has a lambda in it, so we can make it simpler and we can extract the lambda outside of a set of brackets, and we can have that equal to, I'll do it over here. That is equal to lambda outside the bracket. I'll put it at the end. And then we've got m plus a half lambda. Now, I can only emphasize this, that this is the condition for constructive interference with this block of glass reflecting thing. And this looks very similar to that, which is the formula for destructive interference. Thomas, anticipating a good question there. If there are two phase changes, can we just ignore it? Yes, we can. And I'm going to come on to that in a minute, because we'll move on to a different situation when that happens. You're absolutely correct. Okay, good anticipation. So look, you see this on the formula sheet, but you have to look at this particular situation and see, is there a phase change here? And what Thomas has just asked in the chat box, he said, if there was another phase change here, and there were two phase changes, I've crossed that one out, but if there were two, then you end up with an overall phase change of lambda, and that's just a whole wavelength. And the whole wavelength bit then just goes back to this formula, but I'm going to do that in a minute. Okay, so for this particular situation of this glass block reflection, this is the formula for constructive interference. Okay, 2nd is m plus a half lambda, and it's the same as that bit, but with that there. Okay, right. I'm going to now do the destructive interference version of this formula for this particular situation with the glass block and the reflection situation. All right, and I'm going to do that at the top because no, I'm not. Yes, I am. I'm going to do destructive interference, and what's the situation we have going on there? Okay, so what we do is we need to take the formula off the sheet, which is that one, and then we have to consider what's the optical path difference and is there a phase change. Okay, so we'll take the formula off the sheet, just like this formula here is the formula off the sheet. So for destructive interference, the formula off the sheet is OPD equals m plus a half lambda. All right, now what is the optical path difference? Well, we know what it is. It's 2nd. This is the first consideration. 2nd has got to be equal to our formula off the sheet. And is there a phase change overall? And yes, there is a phase change overall. Just like there was there. There it is. There's our phase change. Where does that happen? That happens at the first surface of the block, and I've got a lambda over 2. Now, if I expand that, I go back to basically this, which is m lambda plus lambda over 2. That's the bracket expansion. And then I've got lambda over 2. And these two half wavelengths add together to make a full wavelength, an extra integer wavelength. And so I can ignore these two half steps out of phase, because that makes a whole wave out of phase, which is just not out of phase at all. Okay, so I'm going to rewrite that and say for destructive interference, the formula is, there it is, destructive interference. The overall formula is 2nd equals m lambda, because these two cancel each other out, which may have been what the question was you were asking, Thomas. There's another issue that has exactly two half wavelengths cancelling each other out, and I'll do that, which is what I replied earlier. Okay, so you can forget, disregard these two. Okay, because one wavelength out of phase is not out of phase at all. You're back in phase again. And so there you go. For destructive interference, for this particular case only, I've got two formulae for this particular case only. Now, none of this is a formula on the formula sheet. And you've got to be able to go through this yourself and work out what happens with ray 1. Is there a phase change? Yes, there is. What happens with ray 2? Is there a phase change? No, there isn't. And so overall, I've got a half wavelength difference, phase change overall. What's the optical path difference there and back to ND? Add the two together and see what comes out of it. And it's just a reversal of the formula, mainly because you've got the half wavelength step difference. Okay. Now, what can I do now? I think I ought to do a worked example, because it's no use just looking at all of this and just seeing a whole load of formulae, unless we do a worked example, which will involve either destructive interference or constructive interference. So worked example on this type of light entering a block. And we're going to, instead of having our block sideways like this, with this sort of thing going on, I'm just going to turn it round by 90 degrees, because I want to show you that you can have this in a different orientation, 90 degrees round. It's basically the same thing. And I've got a thin film of glass like this. And I've got a ray of light which comes in and it hits the first surface and it goes off, or it hits the second surface and comes back through. Okay, and I'm not doing all the refractive slight changes in angle. And there is another ray of light which comes out here, but I'm not interested in it because my eye is looking here at what's going on. So this is basically the same as before. It's just a thin piece of glass going off into the distance, or a thin piece of film. And what's a thin piece of film? Well, imagine something like a piece of cling film. And you've got a piece of cling film and you're just holding it out horizontally, and the light reflects off the top and it reflects off the bottom. And do you actually get to see anything or not? Okay, so here we're going to do this. I'm going to give you some information. We'll put some numbers in. So I've got a thin piece of plastic film. So we know its refractive index. It's very similar to glass, 1.6. And thickness, it's very thin. 4.8 micrometers. And light is, this is just fancy physics language. Light is incident on the film. There's incoming light. And the wavelength of the light is 512 nanometers. And the question says, confirm that destructive interference is seen. Right, so what happens? Let's put some letters on. We'll have ray number 1 and ray number 2. Ray 1. So what's the optical path length? We know the optical path length. Whenever a beam of light just bounces off, it isn't going anywhere. It's the second ray that goes further. So the optical path length is 0. That's our first criteria. We'll come and look at optical path difference in a minute. Is there a phase change? And there is phase change. Is our second consideration. And obviously on the outside is air. If it doesn't tell you, you have to assume it's air, where the refractive index is 1. So ray 1, you say to yourself low to high, low refractive index to high refractive index. So for ray 1, is there a phase change? Low to high, I, and there is a phase change. I'll put a tick. And how much is it? It's half a wavelength. Okay, now ray 2. What's the optical path length? It's 2 there and back, 2 times the thickness times the refractive index. Optical path length is 2nd. Is there a phase change? It's inside the material, which has got a high refractive index, and it's air underneath. It doesn't tell you. Must be air surrounding it. It's just like you're standing in your kitchen with a piece of cling film stretched out. There's air above it. There's air below it. Is there a phase change? And so you say to yourself, high inside, high refractive index inside meets low refractive index. High to low, no. Right, so what's the total optical path difference? Well, it's 2nd, and include that as well. What's the criteria for destructive interference? So you have to go back and say to yourself, right, it's actually, who's going to tell me? Who's going to tell me what the criteria is for destructive interference? Just did it, rubbed it all out.
Uh, 2nd equals MD, is it? Or not MD, M lambda?
Yeah, it's 2nd equals M lambda. Okay. Now, why doesn't it have a half? Because the formula on the sheet has a half, and here we've got, I'll stop there before I get too complicated. So it's 2nd equals M lambda. You're quite right, Callum. You're just right. It's written down on the sheet. It's the opposite to the destructive formula from higher. You've just got to swap them over. All right. I'm not going to justify that again because I'll just tie myself in knots. So the criteria for destructive interference is 2nd equals M lambda. Absolutely correct. Okay. So I'm going to go back now and put the formula at the top. 2nd equals M lambda. Right, and I want some numbers. I'm going to put 2 times refractive index is 1.6 Now, the thickness of the film is 4.8 micrometers, which is 4.8 times 10 to the negative 6. Okay, and that's going to be equal to some integer. Now, m can be any number you like, any whole number you like. 1, 2, 57, 6,326. It's got to be a whole number. If it is a whole number, then we have confirmed in this case, it is destructive interference. If it's a whole number, could be any number, don't know what it is. So I want to find out whether it's a whole number or not. So it's m multiplied by, what's the wavelength of the light? 512 nanometers, which is 512 times 10 to the negative 9. So we're going to solve that formula. And if m, in this case, comes out to be an integer, because that's the criteria this time, if it comes out to be an integer number, then it is destructive interference. If it comes out with a half left over, like 6.5 or 3027.5, then we know it's destructive.
Sorry,
Constructive. Go on, sorry.
What's the last number?
512, that's 512 nanometers.
All right, there's no decimal, it's just 512.
Yes.
Okay, thank you.
You want 512.0? Did I just write down 512 nanometers? I think I did. So.
Yeah, you did. Sorry.
Yeah, so I just put in 512. Right, you get your calculators out. And we'll see, for this case, if m is a whole number in this particular case, then it is destructive. If we end up with anything else with a bit of a number left over, then it isn't. So away you go, work that out.
I got m is 30.
Is that a whole number?
Yeah.
It is. Therefore, we've just confirmed that that is destructive interference because it's a whole number and it doesn't have anything left over. All right. This is a bit confusing compared with higher, because at higher we were always looking for a half of a wavelength left over whenever we did problems. But this advanced higher bit, we've got to have the phase change shoved in, which is already half a wavelength. Okay, so this goes back to being an integer number. So this is an integer. It fits into this formula. So it is confirmed. Now what I'll do is I'll say that if you got alternatives, say you got an answer which came out to be exactly any number you like with a half, let's just pick one, 28.5, then that has got half a wavelength left over in the integer. That half shows you that there's half a wavelength left over. So that would show you in this case that you've got constructive interference when you've got half in your integer. That would give you constructive interference. So if you'd done that, if it had said confirm it was constructive interference and the number came out with a half, then it would be constructive interference. But there is also, and I'm just going to point this out to you, there's also a whole load of other numbers. I mean, what happens if you get, that's one alternative. What happens if you get, I don't know, 36.4? What do you think that shows you? Well, it's not a whole number, so it's not destructive. It's not got a half in it, So it's not constructive. Anybody got a clue as to what that could be, or any other number like 73.79? What might those show you? That isn't a 0. It's a 0 there because it's an integer, and it's not a half like that one, which is constructive. So it's neither destructive or constructive. Anybody got a clue what that might show you if you ended up with that sort of number? It's something in between. It's not pure destructive and it's not pure constructive, and that you could call like in between, which is some sort of partial interference, and it's neither one or the other. And I think, in generally speaking, in real life, if you look at the range of numbers you can get, it's a little bit unusual to get a whole number exactly or a half number exactly. You're more likely to get partial interference in real life, and you won't see really, really bright light or really, really no light. You'll just see something in between. And there again, in real life, that piece of cling film, if that's a piece of cling film in the physics question, I think a piece of cling film in reality is probably this sort of thing, and it's got a variable thickness, and you'll get variable numbers, and in some places you would see partial interference. You might see a bit of complete constructive, you might see a little bit of destructive interference, but mainly you're going to see some sort of fuzzy in-betweeny thing where you'll see bands of light that start off bright and fade away to be dark, and you'll get something in the middle. Okay, that's just to throw that one in just in case that comes up. We never did partial interference at higher. It was either one or the other. It was a binary thing. You either get it or you don't get it. Here you either get it or you don't get it, but I think in reality you're going to get something else. Okay, how are we doing? Right. 20 past, still going, still good. Okay, let's have a look. Now, I said before, Thomas, you were saying if you get 2 half wavelengths difference, do they cancel out? And yes, they can. And I'm going to show you how they can do so, not in the way that we've just looked at there, but a different example. So I'm going to choose, this is a second example, no numbers, but can you get 2 half wavelengths cancelling each other out? And yes, the answer is so. I'm going to have some air, and then I'm going to have a thin layer of oil, and then I'm going to have some glass. And I've got a beam of light, of incident light, that's coming down here, and every time there's a boundary, there's going to be some sort of reflection. Okay, so that's going to get reflected, and it's going to come down here, and that's going to get reflected. But down here, this glass is sitting on a solid thing. Okay, a solid thing like a desk. Now look at this. Light travels through air, light travels through oil, light travels through glass. We're going to assume that it's sitting on a desk, and desks don't have a refractive index, and so I'm not interested because it doesn't do anything. You can argue that it does come back and do this, but we're just going to stick with 2 beams of light. Okay, and I'm not really interested in what's on the outside here. Not interested at all because it doesn't ask for it. Now, what are the 3 refractive indices? We've got N is in air, you know that is 1.0. You know that glass is 1.5. And oil, it may not actually say oil in the data sheet because you don't have to remember these numbers. You have to remember that air's got a refractive index of 1, Now, you probably know by now that refractive index of glass is 1.5. You're going to look up the refractive index of oil. It may not say oil. It may say something called glycerol. And I can't remember. I'd have to look this up. But I'm going to tell you that this oil, you're going to have to look it up. It will tell you that the refractive index is 1.45. And we've got 2 beams of light that we're interested in because it tells me I've got 2. So don't go making it more complicated. This is the diagram you've got. You've got ray 1 and you've got ray 2. Okay, now this oil layer has a thickness D, just like it always has done. Right, now let's look at phase changes. I'm not going to give you numbers. I'm just going to talk about phase changes here. Okay, so what phase change at the air oil boundary okay, actually I should have started, yeah, with air oil. This is this first one, so this is ray 1. Right, so we say what's going on? Low to high, high. So there is a phase change at this first boundary for ray 1. And how much is it? If there is a phase change, you know that it's always lambda over 2 is the phase change. Second bit is what is the phase change. Now remember, before we were just doing the beam of light was inside a block or a thin film of plastic or whatever, and this went back to air. Okay, so what's the phase change at the oil glass boundary? This is ray 2. And it's 1.45. It's in oil. It then hits the glass boundary, which is 1.5. So that is low to high, which is I. So what's the phase change? Lambda over 2, half a wavelength. Now, Thomas, you asked the question, what happens if there are 2 phase changes? When it was air outside, there was only one. There was only one phase change at this first interface. But now we've got a phase change there of half a wavelength and a phase change there of half a wavelength. So what's the overall effect, Thomas, of 2 half wavelength phase changes? No change at all, Thomas. Thank you very much. So, because when you add these 2 together, lambda over 2 plus lambda over 2 gives an overall phase change of 1 wavelength. And if you're 1 wavelength out of step, you're not out of step at all. You're only out of step if you're half a wavelength out. Okay, so 2 half wavelengths together mean no overall phase changes on reflection. And then all you've got to do is consider what's the optical path difference. Well, it's nothing there, and it's going to there, and it's going back, and that's 2nd. So the overall effect is, for the optical path difference, is 2nd plus lambda over 2 plus lambda over 2, which is a whole wavelength, so just ignore it. So the optical path difference here is just 2nd. And then you have to say, right, am I going to see constructive interference or am I going to see destructive interference? And then you go back to the formula sheet and you say for constructive interference, it's m lambda, and for destructive interference, it's m plus a half lambda. And that's just completely the opposite of what we just did with the film on its own. Okay, right, Thomas, you've asked me what happens if there's a phase change. Is there a phase change when it doesn't have a refractive index? I don't know, but they're not going to ask you. And the reason why I don't know is because they've never asked me, and I've never thought about it until I thought about it earlier, and you've just said again. So it's not going to happen. You're not going to see a triple. It's a good question. 2 reflections is good enough for all we're doing at advanced higher. If you had this bit of glass sitting on something else with a different refractive index or no refractive index at all, what happens? Not going there because it's not an advanced higher thing. Now, you might say that's a bit of a cop-out, but I genuinely don't know. You'd have to have all 3 phase changes. And what happens if it hits something with no refractive index because it's just a solid thing, like say it's sitting on the ground? Then we're not going to go there. Not going to go there. All right. You'll say that's a cop out, but I've never had to go there, so I don't know the answer. I suppose I'll have to go and look it up now. Or you can go and look it up. I don't know. All right. Just 2 things going on here. They'll give you the diagram. They won't give you it all in writing and say, oh, right, there's oil, air on outside, then oil, then glass, and then it's sitting on the ground, which is a solid. What's going on? They're not going to give you that. They're just going to give you this situation here. Okay. Now you can expand that to any other situation you like. A really common one is air and then some oil. This is what you see in petrol stations. You see like diesel oil. Diesel is a heavier version of petrol. It's just oil. Petrol's really, really light oil. Diesel's heavy oil. It's sometimes called heavy oil. And what happens if you've got in a petrol station, it's raining, you've got air and you've got some diesel sitting on a layer of water, for instance. And then, Thomas, you could still ask me saying it's sitting on some concrete. I don't care. Not that I don't care, that we're not going to go there. So what would you do? You'd have to go and look up, unless they tell you, you're going to have to look up what the refractive index of water is. And if I just have a look, see if I can find a refractive index of water, I think it's 1.33. I'm not exactly certain. Let's see if I can find a refractive index. Can't find it in the data table, so they're going to have to tell you. I'm sure it's 1.33. Oh no, there it is, which is 1.33. Okay, so supposing you get a question in the exam that's got air hitting some oil floating on some water. Okay, you don't need to draw all this down again because you've probably had enough now, but supposing that was water and its refractive index is 1.33, then what happens? Well, you go low to high I, which is half a wavelength, and then you go, oh, that's lower, high to low, no. So you don't, in this case, you don't get another second half wavelength phase change. You've only got the one and you're back to where you were before. You may as well have this as anything less than 1.55, including air, and you go back to like air is 1.0 and it's lower, and you just go back to where you were before, and you have to work it out. You have to say, right, how many phase changes are there? One lambda over 2. All right, so you do 2nd, and then you've got 4 constructive interference, it's m lambda, and then because it's air, I've got another one, so I better add that on, and then you can work it all out if there's a calculation to work out. In this case, you're going to add, in this case, when it's glass and it was 1.5, then you've got to have the 2, so you'd add the extra one in, and then you just say, well, I'm not going to bother because it just adds 1 extra wavelength. It just turns that m into a number that's 1 higher. So you just ignore them and just get rid of them, and you go back there. So you've just got to look at what's the phase change each time. It's on these reflection ones, it's always 2 ND, and then bung in a phase change. If there's 1 phase change, bung it in. And if there's 2 phase changes, leave them out. Right. Would you like me to do one more worked example before we finish, or have you all got to go off for another lesson? Otherwise, I'll have to save a worked example for you to next time. Do you want to do a 10-minute worked example, or do you want to disappear off because you've had enough of me already and you've got something else to do? Tell me what you want to do. Speak to me.
I'm happy to do another example.
Okay. Well, I'll tell you what, if anybody isn't, I'm going to just carry on recording it, and you can just pick up the last 10 minutes out of the recording when I post it up. So let's have a look at another worked example. Now, this worked example is actually in an RGC document, Robert Gordon's College, summary notes and tutorial questions. I think you've probably been using RGC stuff with Mr. Garrett, some questions and summary notes and stuff. Tutorial questions, I'm sure he's been posting them up. There's exactly the same for quanta and waves. There's 2 RGC documents. There's RGC quanta and there's RGC waves, and there's also RGC quanta solutions, and there's also RGC waves solutions. So there's an extra 4 documents inside the quanta and waves main folder, and this is an example taken from there, and I thought I'd just work through it with you. Right, I want you to imagine a glass fiber. There's a glass fiber, it's got a hole in the middle. Okay. Now, whether you get interference or not with light coming in here depends on where the light goes. Does it go through that bit, or does it go through a wider bit? It gets a little bit complicated. So most glass fibers are circular, but the maths gets a little bit, it's not impenetrable, but the maths gets a little bit more awkward. You quite often get these glass fibers, hollow fiber it's called. It's used in insulation materials for roofs and stuff. So it's extruded very thin bits of glass with a hole down the middle, used as insulation material. What we're going to do is we're going to turn our circle, which is a bit awkward, we're going to turn it into a block. We always like turning things into blocks. So we're going to have a fiber of glass with a hole in the middle, and it's a rectangular fiber with a rectangular hole. Okay, so a glass fiber. Okay, so we've got a glass fiber, and we know that the entire length is, what's the entire length? See if I can find it. I'm pretty sure it's 150. Is it 150 micrometers, or is it 150 nanometers? I think it's nanometers. It's a really, really thin fiber. Okay, and I've got this block, this hole in the middle. And the hole is central, and that's 40. And that's 40 nanometers. Okay, right, now this goes back really to my example of a wave in air and a wave in glass, but we're going to make it a little bit more complicated for advanced higher, and we're going to have ray 1, which is totally in air, and ray 2, which is going to go through the glass, then through the air, and then through the glass. So you can imagine that the wave out here is quite long, and then it gets shorter in here, and then it gets longer again in the air, then it gets shorter again, and then it's longer. So the whole thing's changing all the time. Okay. Now, so this is just a little bit more complicated than the plane going into glass. It's going into air and then back into glass again. If you can find this, I'll tell you where it is. It's in the quanta and waves section, and I'll write down where it is so you can come back to it afterwards and have a look at the whole question. So it's in Unit 2, Quanta and Waves. It's in RGC, Advanced Tire Wave Summary Notes and Problems. It's the one I just told you about, which wasn't there before. I just put it in there today, actually. And it's tutorial 3, 3.0 RGC AH Waves Summary Notes and Problems, or Summary Notes and Tutorials, and it's question number 2 in tutorial 3. Okay. Right, and so it's a whole question, and it says, I haven't done this for a bit, so I'm going to say, define the term optical path difference. Define optical path difference. Okay. And that's actually a lot easier than you think it is, because it's a formula that's on the formula sheet. And what is the formula on the formula sheet? The formula is, it just says OPD. It's actually what the formula says is N times GPD. Now, what does that mean? That means that optical path difference is the refractive index times the geometrical path difference. Or you could have optical path length is N times geometrical path length, and you can do what's the path length in air, what's the path difference along here, and you could take the two away from each other, which is what we're going to do. But this is the definition of optical path difference, and you need to write it in words. Optical path difference is refractive index times geometrical path difference, and that's on the formula sheet. And write it in words. Because it says define optical path difference, you should write optical path difference. Here we go. I'll do it quickly. Optical path difference equals refractive index times geometrical path difference. Okay. So what we'll do is we'll have a look at these two rays and we'll say there's an extra bit of this question which I'm going to skip for now, but let's have a look at what is the optical path length between A and B. What's the optical path length between A and B? And then we could actually have it, what's the optical path difference between C and D? And this one's in air, and this one's in glass and air and glass. And then when we take one from the other, you'll get the optical path difference by the time you've done the geometry and multiply by the refractive index. Okay, so The next bit of the question says, what's optical path length? What's optical path length between A and B? What is So it's Ray 2. What's the optical path length? Okay, now optical path length is refractive index times geometrical path length. So let's break it down into bits. Okay, we're only interested in what goes on in this 150 nanometers. Not interested in what goes on out here because it's the same. Not interested in what goes on out here because it's the same. Okay, it's what is going on. The question is just asking us what goes on inside the block. Okay, optical path length is refractive index times geometrical path length. So, okay, let's divide it up. So OPL for AB. You can carry on down here. I'm running out of space. Optical path length for AB. It's in 3 bits. This bit's in glass. So it's N times GPL. That's our general formula, but we've got to do it in 3 bits. We've got to do it for that, and that, and that. Okay, so I've got N, which is, it's glass. I'm sure it's glass, which is 1.5. So I've got 1.5 times 40. It doesn't ask me to do this in meters. I'm just going to leave it in nanometers. 1.5 times 40 for the first bit. And then it's in air. Right, so how long's this bit? Whole lot's 150. So how long's this bit? And what's its refractive index? So that's the first bit of glass, which is there. How long's this bit? Who can work that out? How long's the air? 70. Yeah. And what's the refractive index of air?
It's 1.
Good. So I'm going to add that bit on for the bit in the middle. And then it goes back and it's another 40. And I'm going to add those 3 together. And that total will tell you the optical path length from A to B. 1.5 times 40. Add 1 times 70 and 1.5 times 40. Now 1.5 times 40 is 60, and that's 60. So that's 120, the first 2 bits. Add 70. That must be that it's 190 nanometers altogether. Okay. Now, what is the optical path length? Next bit. OPL for C to D. Anybody work that out?
Just 0?
No, because it's not, it would be if it was reflected, Callum. But
Okay.
no, it's being transmitted. What's it being transmitted through?
Just air.
Okay, what's the refractive index of air?
Just 1.
And how far has it gone?
150 nanometers. Is it?
Right, okay, so the optical path length, OPL, is N times GPL. Remember that? So that's 1.0 times 150, which is 150 nanometers. Last question, that was part B, if you want. Part C is what's the optical path difference? What's the difference between the two of them? Well, the optical path length for the first one, 90. Optical path length for the second one, 150. So the optical path difference is
40.
right. There you go. Now, I'm not going to take up any more of your time now, but there is another bit to do with that question. If you find tutorial 3, question 2, and it wants to know about phase difference, and we haven't touched on phase difference for some time. So I'm going to save the phase difference bit for this question, which came up in a previous bit months ago. I'm going to save the phase difference bit for next time, hopefully. All right. Okay. Now, all I really need you to do is try and learn all that. You could have a look at these RGC tutorials. There's probably some more stuff in the Campbell Robertson tutorials as well. I'll have a look at some numbers. I haven't had time to do this, sorry. And I'll have a look and see if I can post you up some questions. But you're basically supposed to have an hour and a half, and you've had over an hour today, even though I was away chatting to health professionals who just coincided with the beginning of the lesson. Sorry about that. And I'll put something up with some questions that you can do, and you really only need to spend another half an hour tops on this stuff at the moment. Because you've had a load of chat from me, and then you've got your other hour and a half from Mr. Garrett to make your 3 hours for the week. How's that going, Mr. Garrett? Is that all fitting in? Are you managing to spend 3 hours? I hope you are. Anyway,
Yeah.
It's nothing to do with me. It's I'm not looking to see what he's doing, but that's it. So I'm going to stop there. Covered quite a bit today, and we'll be moving on next time. We'll have a look at phase difference for this sort of stuff next time. So I'm going to stop the recording, and I'm going to say, okay, watch out. I will post up some stuff for you to have a look at. Just a few questions, like I did last time, just a few questions for you to have a look at. And again, if you have any problems, I'm grateful if you do have problems that you get back to me. And some people have.